Okay, then we derived the first order rate constant equation. Next we convert this rate constant equation for the first order into a straight line equation. Rearrange this equations to convert into a straight line equation y equal to mx plus c format. Let me rearrange it. I'll take this term and then I'm going to take this term to this side and this term to the left side of this equation. I'll get log a minus x equal to minus k by 2.303 in t plus log a. So this is a straight line form. You see that this is y-axis, this is m slope, and this is in the x-axis plus c. So this is in the straight line equation form. Now I'm going to plot logarithm of a minus x with the time plotted in the x-axis. The slope is actually negative. The slope will be negative sign. Therefore, when time increases, this y-axis log a minus x will decrease. That's what this negative sign says. Therefore, I will get a straight line. If I take slope, this is dy, this is dx. If I take slope equal to dy by dx, this slope equal to k divided by 2.303. So from the slope value, I can find out the k value, rate constant. So slope into 2.303 is the value of k. It's a rate constant of the first order equation. And if I want to find out k value, rate constant of the first order reaction, I have to find out a minus x value at various time. A minus x is the concentration of the reactant at various time is a minus x. So if you measure a minus x at various time t, then if you plot and take a slope, if you plot, you will get a straight line. So if you get a straight line, this indicates the reaction is first order reaction. Then take a slope of the straight line, and from the slope you can find out k value, rate constant. Or simply you substitute in this equation at various time, you substitute a value is the initial value, and also a minus x is as I said, a minus x is a concentration of the reactant at various time. If you substitute in this equation, you can find out k value. So this rate constant k value can be either determined using this equation or by graphically plotting log a minus x versus time t. So this is about the first order equations, first order reactions, the important characters of first order reactions. Next, I would like to explain a few problems. Let me here. The problem is A data is given here at various time. They have given a volume of KMnO4 in ml. So they are asking us to calculate to find out you are asked to find out to show that the decomposition of hydrogen peroxide in aqueous solution is first order from these data. So hydrogen peroxide in aqueous solution is decomposed. Usually this is decomposed into water and oxygen. So this decomposition reaction, of course, you need catalyst, either light, or you need a catalyst. Maybe I'll take platinum. So this is a decomposition reaction. So you are carrying out this reaction, and these are the observed experimental data. You have to show that this reaction is first order using this data. I mean, what the experiment that you usually do is you have to take a reaction bottle. You have to take a reaction bottle. Within this, you have a hydrogen peroxide and of course platinum. For example, platinum as a catalyst. If you do this, this is converted into water plus oxygen gas is formed. Oxygen gas is evolved. A simple reaction is taking place. Now you take the reaction mixture, maybe some about 10 ml. You take this reaction mixture. 10 ml of the reaction mixture is taken out from this reaction bottle, and most probably you have to arrest the reaction. That means you have to stop the reaction. Further, the reaction should not proceed when you take out this 10 ml from the reaction mixture at time, let me say at 0 time. Then the reaction mixture, this is taken into a conical flask, and this is titrated with the KMnO4 taken in the burette. So this is a simple experiment. So at various time interval, 0 time, you are taking out the reaction mixture, the reaction mixture, the content of the reaction that you are carrying out in this reaction bottle. You are taking out the content about 10 ml, then transferring into a conical flask where the reaction must be arrested, that the reaction must be stopped. Then the reaction mixture is titrated with KMnO4 taken in the burette. And then this is, let me say, 0 time. So this is 0 time that the reaction has not proceeded. So the 0 time, you have measured the volume of KMnO4 required. It is 22 ml. Then at 300 seconds, at 300th second, again you are taking out 10 ml of the reaction mixture, transferring into conical flask. Then you have to stop the reaction by adding ice or some other method that you are arresting the reaction, and then you are titrating with KMnO4. Here the KMnO4 consumed the volume required to react hydrogen peroxide. All the molecules of hydrogen peroxide taken in the conical flask is 17.7 ml. So at 600 second, again you are taking out 10 ml, then it is transferred into conical flask, and the reaction is arrested here and it is titrated with KMnO4. The volume required to react with this hydrogen peroxide molecules present in the conical flask is determined. It is 13.8 ml. So this is how the experiment is carried out. And this is a simple data that you observed from doing this reactions. You have to show the reaction is first order, that this reaction is first order. What I'm going to do, I'm taking this first order equation. Here A is, I said, it's the initial concentration. I said I said this 22.8 ml is the amount of KMnO4 required to react with the hydrogen peroxide taken in the conical flask at the beginning or at the zero time. This is actually, A is actually directly proportional to volume of KMnO4. This is initial concentration of hydrogen peroxide will be directly proportional to volume required. If higher the initial concentration, the volume required will be more. It is directly proportional to volume of KMnO4. Volume of KMnO4. So at zero time, this is zero time. That is, you just added hydrogen peroxide with platinum. That's all. So as soon as you mix this two, hydrogen peroxide with platinum, then you have to take 10 ml of the mixture, then you have to stop the reaction. The reaction should not start. That is called zero time. So at the zero time, the initial concentration A will be directly proportional to the volume required from the burette. And at various time, say at A minus X, A minus X is actually directly proportional to the volume required. Result A minus X is actually directly proportional to 17.7 ml at 300 second. A minus X is actually the reactant concentration. The reactant is hydrogen peroxide. So A minus X is reactant concentration is varied time. So at the 300th second, the reactant concentration A minus X is directly proportional to the amount of KMnO4, volume of KMnO4 required. So at the 600 second, the A minus X value is directly proportional to 13.8 and so on. Let me first use these data, first two data. I'll use this first two data to find out K value. K equal to L, let it be 1, so 2.303. Time is the 300 second. The initial concentration, as I said, is directly proportional to volume of KMnO4 at 0 second. So initial concentration will be 22.8, and A minus X at 300 second is 17.7. So to find out this value, if you find out, you will get 8.4414 into 10 power minus 4. This is first order kinetics, and the K unit of K will be second inverse. and I'm using third data again, 2.303 at the third. Here the time is at the 600 minute at 600 second. The volume required is the initial concentration, that is A is 22.8, and then at the 600 second the volume of KMNO4 required is 13.8 ml, and then work it out, I'll get 8.3697 into 10 power minus 4 second inverse. And the third data, here I'll take 900.303 at 900 second. The initial concentration is directly proportional to volume of KMNO4 required at 0 second, that is 22.8 divided by A minus X value is 10.6, and this value is again 8.5100 into 10 power minus 4 second inverse. Then the fourth data, here at the 1200 second volume of KMNO4 8.2. Therefore it is 2.303 divided by 1200 second, log of initial volume is 22.8 into 8.2. If you work out, you get 8.5218 into 10 power minus 4 second inverse. So from these data, I just calculated K value at various time, 300, 600, 900. The value here is 8.4 in 10 power minus 4, 8.36 10 power minus 4, 8.5 into 10 power minus 4. In the fourth, it is K value is again 8.5 into 10 power minus 4. So the value is around 8.5. The K value rate constant of hydrogen peroxide decomposition reaction at particular temperature is constant, and it is about 8.5 into 10 power minus 4 second. So it is a constant value. It is a constant. So right, this is a constant at various time. So this constant value shows that the reaction is first order reaction. I mean, this reaction, the decomposition reaction using in aqueous medium, using catalyst, then this decomposition reaction is a first order reaction.